algebra fans. This is a lesson about simplifying radicals. One thing you need to know about radicals, which we haven't really talked about too much yet, is what all the different parts of it mean and what all the different parts of it are. Okay, radicals that you're used to now is square roots, right? Today we're dealing with square roots, but there are also other roots, the cube root, the fourth root. So let's talk about what that looks like when we do other roots, which you're probably not used to yet. First off, terminology. The parts of the radical are this check thing. That's actually the radical. That's officially the radical, although that's not how everybody uses it. Then the line going across the top of your number is called a vinculum. Although hardly anybody calls it that. We generally just talk about the whole thing as a radical. So, or sometimes we'll say under the radical or that kind of stuff. And so we do it a little bit more freely than it is officially. So the radical is officially a check. The vinculum is a line that goes, oh, by the way, a line going over the top of stuff, delineating what's in the group, is used more often. For example, you're probably used to seeing it as a repeating decimal line. That one's also called a vinculum. It's just a line that's on top of a set of numbers to in some way group them or let you know something about them. The number that's inside, say if there's a number in here, that's called the radicand. So, a few things. We need to, let's talk a little bit about how the different ones work. Oh, let me show you this first. This is going, if it's a square root, there's really supposed to be a 2 there. You're saying, well, why would there be a 2 there? It's a square root. Yeah, okay. Well, what we have is the square root. Let's think back. What does it mean to be the square root? What is a square root? A square root. Okay, well, what if I have 9 and I take the square root of 9? What's that? 3. Yes, yes. I saw somebody say that. One of y'all. Who was it? Must have been Olivia. Okay. Square root of 9 is 3. Okay, so this is 3. So what if I take 3 and square it? Then what do I get? 9. Okay, so now this is 9. Okay, this is all 9. What if I take the square root of all that? Okay, well now it's 3, right? Because that was 9. That all simplifies to 9. Square root of 9 is 3. So now it's 3. Okay, so I'll square it. Okay, so now it's 9 because it's 3 squared. Okay, so I'll take the square root of that. That was 9. The square root of it is 3. Okay, square all that. And so the square of that is 9. Okay, so now it's 9 with all this junk in it, all these nested groups. All right, and then I take the square root of that and I'm back to 3. What am I illustrating here? I'm illustrating that it flips back and forth. It's kind of like a little toggle switch, okay? So you have the square, square root, squared, unsquared, squared, unsquared. Unsquared is not a word. It's not a word, but it works. Squared, unsquared, squared, unsquared. Square it, take the square root of it. Okay, well, how does that work with other things? If we look at this, the 9 was 3 times 3, right? This original 9 was 3 times 3. Does this yellow show up? Shows up kind of. So this original 9 was 3 times 3. It was already 3 squared. So what we did is we took 3 and we squared it and we unsquared it. And we squared it and we unsquared it. Okay, let's remind ourselves and we get back to 3. You start with 3, you square it, you unsquare it, you square it, you unsquare it. You're going to get back to 3. You're going to toggle between the perfect square, which is the number that's whose square root is the whole number, and its square, perfect square, and the root. Okay. Well, okay. Let me think. It's called the square root. What do I know about a square? Okay, square is length times width. And since they're the same, say if that's 3 and that's 3, then length times width as the factors will give us 9 for the area. So one representation of what we're doing here is relating the dimensions, 2 dimensions, and each of them what they are to get the area of it. That's why it has a special name. That's why it's called square root, because it's useful. It exists in real life and real people use it, as opposed to just mathematicians who are special people. Okay. Also engineers. Also lots of people use this stuff actually. Okay, so what do I have here? So I have the square root of 3 times 3, or the square root of 3 squared, or the square root of 9. Okay, so I took a 3, I squared it. There are 2 3's here. Remember, squared is just the lazy mathematician shorthand of saying, I'm tired of writing 3's, I'm just going to write 2 of them. When I take the square root, I go back to 1. There should officially be a 2 here that says that what we're doing is looking for pairs like this. Okay. So it also works, by the way, if you could do it with more of them. For example, if you have 3 cubed, 3 cubed is 3 times 3 times 3. So we'd be saying, what do you multiply by itself 3 times to get 27? Here we said, what do you multiply by itself and use it as a factor 2 times and get 9? Here we're saying, what do you multiply by itself and use it 3 times as a factor and get 27? Okay? So this is the cube root. We'll put a 3 there to say which root we want. This little radical is just telling us we're going to have one of the roots. In this case, it's the 2, and here it's the 3. So what we'll have here then is, again, what if I want to know the cube root of 27, then I say, what number do you multiply and use it as a factor 3 times, and you get 27. The answer is 3. Because 3 times 3 times 3. What's the cube root of 8? 2 times 2 times 2. The cube root of 8 is 2. Okay. So it's the same deal. Now the default is, if there is no number in the check, it's a square root. It should be a 2. Officially, there should always be a 2 there, but we hardly ever put it. You have to put it with the higher powers, because otherwise it looks like the default, which is square root. And a reminder, I think I've mentioned this before, there's no special name for the 4th and the 5th and all the other powers. So you just call it the 4th power, or in this case, the 4th root. So for example, if you have the 4th root of 16, that's going to be 2. What do you multiply by itself? Use it as a factor 4 times, and you get 16. Well, 2 is what you multiply. Okay? All right. Okay. A reminder, a perfect square. What is a perfect square? It's a really handsome square. No, although it could be. A perfect square is a number whose square root is a whole number. Positive, of course. Is a positive integer. Okay, well, actually the negative would work too, but we're just dealing with the positives, because negative 2 times negative 2 is still 4. There's 2 perfect roots. Let's just say integer. Either one. Either one work. Okay. When we simplify radicals, we want, I'm just going to tell you a little bit about it, and then we'll get into it. And that is, a simplified radical has no perfect squares, no perfect squares, and no radicals in the denominator. Yeah, I'm going to go through this for a while, and then denominator. When it's a simplified radical, there's no perfect squares, and there's no radicals in the denominator. I'll talk about this more as we go along. So, for example, if you have the square root of 20, there can be no perfect squares under the radical. You look at that and you say, well, duh, that's done. 20 is not a perfect square. It's 5 times 4. It's not going to be a perfect square. Oh, but wait. There's a stealth one here. There's one hiding from you. You must seek it out. Okay. Let's write all of the things that multiply to get 20. Well, 2 and 10, 4 and 5, 1 and 20. Okay. I want prime numbers only. So I'll say 2 times 2 times 5, or 4 times 5, or 2 times 10. So everybody see that that is 20. This is what you can't have. This is a hidden perfect square. This is a perfect square. It is 4. A simplified radical cannot contain a perfect square. So we can rewrite this as the square root of 2 times 2 times the square root of 5. You're allowed to do that. We'll talk more about it here in a moment. But for right now, you can just kind of watch. Okay, what is the square root of 2 times 2? Well, it's 2 squared and unsquared, so it's back to 2. And then the square root of 5. Up to this point, when you've been given square roots for answers, you've a lot left to put them into decimals. We're not going to be doing that. We're going to be learning to do it exactly. The decimal is always an approximation for a radical. It's never accurate. So in many cases, we need to work with the accurate ones, so you need to learn how to do it. Okay. Now, if you start to think about it, you're going to see that this is a problem. Because you're used to finding factors like you'll say, what are the factors of 12? And you'll go, oh, 6 times 2. And you'll say that's 3 times 2. And that's, okay. And so that you can find out the prime factors here. You've done that in 6th and 7th grade. Okay, but now we're not in 6th grade anymore. We have bigger numbers. And I want to show you a way that works. And it's called short division. Okay. Short division is a technique that my mother taught me like in 2nd grade. But my 2nd grade teacher and 3rd grade teacher and 4th grade teacher wouldn't let me use it. You know why? They weren't wrong, but you know why? Because you don't show your work. So, but you know what? I'm not in 2nd grade anymore, and I can decide when to show my work. And for this circumstance, you don't have to show your work either, but to do it this way. So let's start with comparing what's short division and what's long division. Okay, regular long division. I'm going to divide by 308. I want to divide 318 by 2. Okay? That's long division. Here's the short division. I'm still going to write 318 in a division sign, but it's going to be upside down. How clever. And I'll still put the 2 out to the sides. Let's look at what happens. First off, I say, how many 2's are in 3? Oh, there's 1. 1 times 2 is 2. 3 minus 2 is 1. Okay. You are all proud 8th graders, and I'm just really confident that you can do 3 minus 2 and get 1 and do it in your head. So, let's do it. Come over here. We're going to do it upside down. The answer is going to be on the bottom, still on the top. So now then, how many 2's are in 3? 1. After you took that 1, 2 out, what was left over? 1. We're going to put the remainder right there. We're going to write it little bitty like that to remind ourselves what it is, and always write it. Don't just have it in your head. Okay? So now then, and why did I do that way? Well, look back over here what happens. What is my next thing? I'm going to divide into this. What I got to do, I got to bring down the 1, right? But notice where this number came from. I'm going to divide 2 into 11. Where did the 11 come from? The first digit was the remainder, and the second digit I just brought down. Look right here. I stuck my remainder next to my next digit, and I'm done. I didn't have to write all this. Okay? So now then, we'll come back to the long way and say, how many 2's are in 11? 5. 5 times 2 is 10. 11 minus 10 is 1. Again, I'm confident that you can say 11 minus 10 and get 1. If you can't, we've got other problems. Okay, so now then, I'm going to sit over here. I know that's my remainder thing. I remember from here that the next number that I divide into is the remainder and the next number. I've already got the remainder and the next number. How many 2's are 11? 5. After you took those 5 2's out of 11, what was left? 1. Stick it right up there. So now it's going to go with the 18. Again, over here, same deal. Bring down my 8. How many 2's are in 18? 9. 9 times 2 is 18. 18 minus 18 is 0. I'm real sure you can subtract 18 from 18 and get 0. You don't have to show that work. Okay. All right, so now then, how many 2's are in 18? 9. You're done. So that's short division. Okay. Here, you try a couple of them. Do 172 divided by 2 with short division. Do 267 divided by 3 with short division. Do 2,675 divided by 5. Okay. Remember to write your little remainders above. Okay, now how to use this. This is going to come in really handy. Remember how you used to do the factor trees? I just did a factor tree and it works just fine for 12. But we're going to need to do something a little bit better for one of them. If you would, go ahead and write these steps down and I'll go through with you what they mean. So, okay. Pause it and then get back to me and we'll write it down. Here's how we go. We're going to find the prime factors of 72 by using short division. Okay, since we want prime numbers only, we only want the prime factors, we'll only divide by prime numbers. So I won't divide this by 4 or 8 or 9 because I know all of those, or even 12, because I know all of those, I know all those would work, but I'm not going to do it because they're not prime numbers. I always start with the smallest prime number because it's the easiest. 2. How many 2's are in 7? 2, 1. I just did that wrong. 3, sorry. 36. Okay? If it is still even, remember all even numbers will divide by 2. If it's still even, let's look. We can do it again. We don't have to write it all over or anything. Divide by 2 again. Get 18. Look, 18 is still even. I'm going to divide by 2 again. Okay, now it's odd. It'll divide by 3. 3 times 3 is 9. Reminder, how do you know if a number will divide by 3? You add up the digits. That's that funny little rule. Add up the digits, and if the sum of the digits is divisible by 3, then the original number is divisible by 3. Okay. 9 divided by 3 is 3, and 3 divided by 3 is 1, and you do this until you get 1. Once you've done that, these are the prime factors of the of 72. Okay. Well, let's look at how that works for our thing today, which is radicals. Okay, on radicals, so if I want to simplify the square root of 72, the square root of 72 equals the square root of 2 times 2 times 2 times 3 times 3. 2 times 2 times 2 times 3 times 3. We can split these up into individual radicals. The square root of 2 times 2. There's 2 of them. It's the square root, the second power. You square it, you unsquare it. Then times the square root of 2. Then times the square root of 3 times 3. Now what am I doing here? I've put them into nice little happy couples and the lonely only. So the happy couple of 2's is here under the radical house. The happy couple of 3's is here under the radical house. What's the square root of 2 times 2? Well, you take 2, you square it, and you unsquare it. It's 2. The square root of 2 is just the square root of 2. There's no perfect square. 3 squared unsquared is, 3. So what do we have now? Now, how we write things, we put all of the numbers in the front that are multiplying. So this will be 2 times 3 times the square root of 2. We just never put it at the end. It's not wrong because multiplication is commutative. It just looks strange. We just don't do that. Okay? We just don't do it. Okay. So this will be 6 times the square root of 2. That is the correctly written, simplified square root of 2. Okay, let's talk a little bit about this. What did we just do? I have another one here. I'll do this first, okay. So, what I just talked about is this, how to write a radical. So make sure that you make a note of this, and then I'll go on. All the outside numbers down the outside, the inside, and you arrange it so they're written together. So here's an example of that. Okay. Here we have, so I'm going to multiply 2 times the square root of 3 times 5 times the square root of 7. When I put it together, I'll put all of the outside numbers, the ones that are not square rooted, not under the radical, together, and then I'll arrange the ones that are under the radical together. And then I'm allowed to put these together to simplify and put these together. Here's the principle that allows us to do it. I think you've already been doing some of those, but you may not have. But make sure you make a note of this. The product of the radicals is the radical of the product. The quotient of the radicals is the radical of the quotient. Okay, you might want to pause and write that down. Let's look at how we do some of these. Okay, you can also do it with letters. Remember, if you have a happy couple. Well, here, let's talk about what I'm talking about, happy couple. Let me look back and let's do the square root of, I didn't my calculator. How about, we'll just do 72. We already know 72 is the square root of 2 times 2 times 2 times 3 times 3. Okay, well, the way I like to think of this, as I mentioned a little bit earlier, I alluded to, is happy couples and lonely onlys. So what we'll have here is a happy couple of 2's. And the happy couple of 2's goes out on the town. They're going to have a nice evening out. When they arrive at the restaurant, the maitre d' says, "Oh, Madame Tu looks so beautiful tonight. I am so glad you are here, Tu family." And so it's the Tu family. And so once they're out of the town, once they're out of the radical house, they're now referred to as the Tu family. Okay. Same deal for the happy couples of 3's. Happy couple of 3's. "Oh, Madame 3, you look lovely tonight. Monsieur is so debonair." Okay. And so the happy couples of 3's come out of the radical house. And the lonely only stays home and watches Netflix. So happy couples go out on the town. They leave the radical house. The lonely only stay home at the radical house and pop popcorn and watch Netflix. Okay. It's so much more fun to do these with y'all there. I've been seeing y'all. It's more fun to crack these stupid jokes when y'all are there. Okay, let's look at a few of these and see how to do them. Okay, what you're going to always want to do is get the happy couples away. Happy couples must go away. Okay, so here's an example, the square root of 48. Everybody do it. Find the prime factors of 48. Look, I'm done, and I'm old. Hopefully you're done. So the square root of 48 is the square root of 2 times 2 times 2 times 2 times 3. Happy couples of 2's. Another happy couples of 2's. I wonder if they're cousins. And 3 is a lonely only. So now we can rewrite that as 2 times the square root of 3. And remember that we'll go ahead and simplify that to 4 times the square root of 3. What if there is a variable in it? Let's look here. The square root of 4x squared. Okay, well, let's write it out as factors. Of course, 4 is 2 times 2. And x is x times x. Oh, look. Happy couple of 2's. Happy couple of x's. And no lonely onlys. So that'll just be 2x. 2x is the square root of 4x squared. Okay, how about this one? The square root of 4 over 49. The product of the radical is the radical of the product, and the quotient of the radical is the radical of the quotient. So we can write this as two separate ones. We can say that this is the square root of 4 over the square root of 49. Square root of 4 is 2, square root of 49 is 7. So the square root of 4 over 49 is 2/7. Another one, how about 32m to the 5th? Take the square root of that. 32, that's 2 times 2 times 2. 2 times 2 is 4. 8, 16, 32. That's 5 2's. 5 2's. 2, 4, 8, 16, 32. And lots of n's. Okay? Happy couples of 2's. Happy couple of 2's. Happy couple of m's. Another happy couple of m's. A lonely only 2 and a lonely only m. So what do we have left? M times 2 times 2 times the square root of 2m. This will simplify to, 4m squared times the square root of 2m. This is the final answer. Okay? Now you're starting to notice you can't get a decimal out of that because it's got a variable in it. So we're going to have to work them as radicals. Okay, work a few more of these. I just worked some of them. Pause it for a while and work as many of them as you can think of to where you'll get comfortable to it. Okay, pause it. And here are the answers. Be sure to check how you're doing. And we're going to stop here because this is getting kind of long. Okay, so there's another lesson in this. It's rationalizing the denominator, and you'll need to look that one up too, please.